Okay, thank you very much, Pietro, for the invitation. Thank you very much to all of you for coming. Well, the idea is to talk about something called fusion categories, but maybe I will go more to fusion rings. And in the construction, I will show what that means. And the idea is just another way to understand these objects using the right categories. That was really nice because this category is related with quantum groups and all of this stuff. You can construct invariants for tree manifolds, for nodes, and so there is some topological applications. And for that reason, some people want to understand this. And right now, too many people is working in this because this is like an analog of group theory, but in the categorical level. So the idea is that I will start with a semi-simple complex Lie algebra. Maybe I need that to fix just for this semi-simple complex Lie algebra. We have some Cartan matrix from I to j, from 1 up to n. This is the Cartan matrix. If it is not symmetric, then we need to consider some diagonal matrix, G1 up to Gn, such that G times A is symmetric. I just need this in definition, but it's not crucial. Just to fix notations, it's what I want to do. And the ring in which I'm going to work is rational functions over C, where B is just a variable. What I want to is to define a new object, which is called a quantum group or quantized enveloping algebra, which depends on this B. If you change B, then you can recover the usual enveloping algebra. And the nice case, which is the one that I want to work, is when I replace B or specialize B to a root of unity. In this case, the representation theory of this object is going to change, and is more similar to algebraic groups, infinite characteristic, which is really nice. I will show you examples mainly in SL2, some examples, some ideas, and maybe in SL3 just some pictures. So the main object I'm going to work, which I denote like this is what it's called the quantum group or quantum enveloping algebra. And what is this? This is an associative algebra. Over these rings of rational functions. This could be rational numbers. There is no trouble. But just to do the things easier, I will work there. It is generated. This is over this with unity, with unit generated by some elements that I denote EI, FI, and KI plus minus 1. These are just the usual E and F for the Lie algebra. And this is going to be something like E to the B for some Cartan generator, something like this. But it's better to work with this guy. And they are subject to some relations, which are just the quantizations of the relations for the semi-simple Lie algebra. Basically, they are, for example, the ones that are important is that these operators are commutative. And when I act with the inverse, of course, I get the 1 in both sides. Also, the one that allows to compute the weights in your representation, this is a highest weight theory, is that the action of this Ki on the E, and Ki again, maybe I can put I, J, A inverse, this is just this variable to the diaij ei. For that reason, I just need this. And here, if I replace with this f, I put a minus here. And the other one is, sorry? J. And also, I have this one, ei, fj minus fj ei, which is the usual bracket which gives you the h in the semi-simple case. In this situation, I don't get the h, but something related with the case, which is ki minus ki inverse b minus b inverse. I need to put maybe some I, or this is to the power of gi. Doesn't matter for the moment. Let's say this. And delta the ij, which is the Kronecker delta of these two. Plus some quantization of these set relations, which are not important in my case, so I don't going to write it. In a specific situation, for example, for SL2, this quantum envelope in algebra is generated by operator E, F, K, K inverse, and it satisfies that E, F minus F, E is equal to K minus K inverse, B, B inverse. This K, E, K inverse is B to the 2, E, and K, F, K inverse is B to the minus 2, F. And this is just, for example, in the SL2 case, the simplest case. We don't have this set relation, so this is good enough for us. When I want to replace the variable v to a number, it's not just to literally replace. I need to do some tricks. If this parameter, I want to replace it, for example, for a complex number, which is not a root of unity, I can just do it, and nothing happens. The problem is that my coefficients are over this guy. So in principle, I have functions of this sort, where I said it's complex number, so I need to take care with this. So I need to erase rational functions and consider something else in which I can replace. There are no troubles, no singularities, and then I go again to this algebra. For that reason, I need to consider some integral forms. The integral forms for the quantum group. And the one that I am interested in is in the Lustig version. For this version, I need to define what is called the divided powers. And divided powers are new generators defined in terms of these guys, which I denote E, for example, I, to power n, in this parenthesis, which by definition is E to power n divided by this n factorial. And this number, in brackets, it's called a quantum number for any number, let's say n, is just b to the n minus b to the minus n over b minus b inverse. And if I put a factorial, is what you can imagine. This factorial is n times n minus 1, 2, 1. We can define binomial coefficients and all of classical numbers, but now with this definition of this variable. The same for the f. You can define this divided power, fi to the n factorial, and in a moment I will show you why I need these guys. And then I consider something that I will call U. Sorry, I consider this ring. Let's consider A is just Laurent polynomials with integer coefficients. Using this as my new base ring, I will define UA as the subalgebra of my enveloping algebra, quantum enveloping algebra, which is generated generated by both case with the inverse and the divided powers, ei to the n and fi to the n. This is my new algebra with these generators, extra generators, new generators. You can show, it's possible to show that like one of these properties of these guys is that UA, when I tensor over A with this guy, is indeed isomorphic to my enveloping algebra. This is nothing, this is good, and this theorem is the one that will allows me to replace this V for the number that I want, and this is done. Because if I replace this by a number, this is just the complex numbers, but in this ring, there are no divisions, there is nothing happens, so I don't have the troubles, for example, that I have in this case, as I told you, of this kind of functions, which produce division by 0. So I don't have this in this case. And using this, I can consider the following then. If Q, it's a complex numbers, which is not 0, and I consider C as an A algebra by the action over the map which A is sent to C, the variable B, I just sent it to this number Q. I'm replacing this algebra structure over the complex numbers is saying you can replace this guy V by Q. If I consider this, then I can produce this new tensor product over A. Just C. This considered as an A algebra with this action. This is an A subalgebra, so everything is okay. And by definition, this is my quantum group when I specialize Q to a specific complex number or a specific parameter. The nice things on this are the following. One thing that I don't told you is that this is not just an associative algebra, this is a half algebra. There is more structure in it. This is a half subalgebra of this guy, but I don't need the half structure for the moment, so for that reason I'm not talking about that. And I don't need any half formula, so it's not important for the moment. For the moment, what I need that you know or recall is who is this enveloping algebras and all of this stuff. The property, or their nice property, are the following. Is that this, just one notation. I will denote, let U, this curvy U, is just the category. Category of finite dimensional modules over my enveloping algebra. You can ask, could you consider infinite dimensional modules? Yes, but then I need to consider something called integrable modules. Integrable modules, why? Because there are modules in which the actions of the case is kind of diagonal action, but at some point the action of the E and the F is nilpotent. This nilpotency allows you in some sense to recover a group, if you can do it. But this is the integrability. But I don't need this big category to consider these ones. So I need the finite dimensional modules. And when I consider finite dimensional modules, there is a nice property which says that U is a semi-simple category. That means any module is isomorphic to a direct sum of simples. If I have a semi-simple category, U is semi-simple category if and only if this number Q is not a number Q in Z minus 0, is not a root of unity, or is different from plus or minus 1. Because like in this case, you are going to recover the usual category, and if it is any possible number or a generic variable, but it's not a root of unity, then this one is a semi-simple category, because this one is the category of finite dimensional modules. What I'm saying is that in this situation, when Q, let's say, is not 0, neither 1, and not a root of unity, not root of unity, then the category U of finite dimensional modules over my quantum group is just equivalent to the category of finite dimensional modules over G. So this is the usual representation theory, you know, for a semi-simple algebra. This is known, so this one is known. So this is not an interesting case. For that reason, I want to go to this case. And what happened in the root of unity case is now my category is not semi-simple. And if the category is not semi-simple, it's more interesting than just in this one. So let's fix Q to be a root of unity. And let's see what happens and what is going to change and what can we produce. So let Q to be a root of unity. Moreover, I will say Q to the L. L is the order of my root. It's going to be 1. And I will fix L to be an odd number. Could be even, yes, of course, but you need to redo everything more carefully when it's an even number. So it's better to work with the odd root of unity case just for simplicity. But the results hold in general. So this category now is not semi-simple. And something is happening. And I will show you how it's happening in an example before to give you some properties. So this is one example in SL2. Usual SL2, not just quantum SL2, nothing. Usual SL2. In SL2, we know that we have the simple modules. Simple modules, which are something just Ln, and n is a non-negative integer. These are all the simple modules. For these modules, I can, for example, let's say L3. Who is L3? It's a 4-dimensional module. 1, 2, 3, 4. Let's say this is called B0, B1, B2, B3. In the usual Lie algebra, we have a generators, little e, little f, little h. We have diagonal action. The action of h on this one is given by multiple of 3. This one is 1. This one is -1. This one is -3. We have the generators in one side. Starting with this one, which is the highest weight. I go, the action in this direction are the f's, the e's, the f's. The action in the other direction are the e's. So if I start with this guy, we have something like this. The same for the e's. But these guys are all of them are different from 0. This is, you can rescale something like this is 1, 2, 3. This is 1, 2, 3. This is the action of E on this one. On this guy, just B2. The action of E on this guy is twice B1, and so on. This is an irreducible module in the usual case of SL2. What happened in the generic case for a quantum group? If you think in this guy now, UV SL2, it is possible to quantize this guy. And to quantize this guy is same picture, same module. This is done by Lustig, and Lustig showed that this picture I'm going to draw here, to quantize to this one. So I have the action. Let's call again B0, B1, B2, B3. Now the action, the diagonal action of the case, these loops are the case, is not 3, 1, -1, -3, but it's Q to the 3, Q to the 1, Q to the -1, and Q to the -3. I have also the action of the F's, now my big F, capital F, but this is with the quantum numbers, 1, 2, and 3. And also my action of the is, which is 1 in here, 2 in here, and 3 in here. In this case, if this is just generic or satisfies any of these conditions, it's just complex number, which is not root of unity or different from plus minus 1, you can play in this algebra with these generators. Nothing happens. These guys are always different from 0. So this module is exactly the same. With different coefficients, exactly the same module, irreducible. Nothing happens. But when I have in the root of unity case, and that's the reason I need to use these divided powers generators. Now, if we specialize B to Q, where Q, let's say to the 3, it's equal to 1, what's happening in this module? Now in my algebra, UQ picture in principle is the same. B0, B1, B2, B3. The actions, the diagonal actions, is no problem. Q to the 3, Q, Q to the minus 1, and Q to the minus 3. But the problem is that this guy and this guy become 0. They're vanishes. So now I have, this is okay, it's 1. This is okay, it's 2. But this one is 0. And in the other direction, this is okay, is 1. This is okay, it's 2. And this one is 0. Now this module, for a root of unity parameter, is not irreducible, but it's an indecomposable module. In this module, this part is a submodule. And this guy is a quotient. What's happening? If you start with this guy, you can go here, here, but don't here. So you are missing information. You need something extra. What I'm saying is this guy don't generate the module if I just think in this picture. But if I add the new extra generators, which are the divided power generators, let me just erase these lines for a moment. If I add the divided powers, I can jump in a step of order of the root of unity. So this is the action, for example, of E3 when I go in this direction, or is the action of F to the 3 when I go in the opposite direction. If I apply to this guy, F to the 3, I start to landing here. So with this guy, I generate the module. It is a cyclic module. This line is just F to the 1, which coincides with F to the 1, just a multiple of F to the 1. This is F to the 2 in parentheses, which is just a multiple of F, the usual power, square power. This disappears, so I need an extra guy. This extra guy allows me to jump. In the other direction, I can't to jump again. So for this module, I can extract. Let's denote this module. Now it's not called ELD. I put another name, delta 3. And for this delta 3, I extract one module, which is now the simple module, L3. And this L3 is just this guy and this guy, which is the simple module with weight 3, Q to the 3. And this is just B0, B3. This is weight 3, weight minus 3. And the action in one direction and in the other direction is the divided power generator. For that reason, I need in the root of unity these guys. If I don't have these guys, this is not a cyclic module, and I'm not producing everything. This is one of the reasons. Moreover, in the root of unity case, this operator is 0. Why? Because this is just the quantum number of 3 applied to e to the 3. This becomes 0, so this guy is 0. So I need this extra generator. This is one of the reasons I need to use these two guys to produce the module. This is a two-dimensional module with weight 3. But this little part here is a submodule. It's also irreducible. So I have also L1, which is B1, B2, the usual action, these two guys, just 2 and 2. But this is of weight 1. So this is the irreducible module of weight 1, dimension 2. Irreducible module of weight 3, dimension 2 again. So now dimension is not something that can classify the irreducible modules, as happens in the usual semi-simple case. Then the things start to changing. You can dualize this module. Dualize the module just means put the arrows in the other direction, and then you get the dual of this guy. And in the dual of this guy, you will get this one is a submodule, and this one is the quotient module. And you can start to playing around with these modules. These blocks, these deltas. Yep.
Sorry, so UQ is the quantum group with divided powers?
Yeah, this one.
So as a module of the net algebra, this four-dimensional thing, you call it delta 3, and it's irreducible?
It's not irreducible, it's indecomposable.
But UQ includes the divided powers, right?
This one includes the divided powers, but they are useful in the root of unity case. If you are in the generic case, you have this picture, which is irreducible. So in this picture, of course, you also have the divided powers, because any of these guys is 0. So you have the divided powers. But when you specialize to a root of unity case, you need something extra information. And for that reason, you specialize in Lustig form with divided powers to get this.
Yeah,
this.
But this module is irreducible over the algebra with divided powers.
Over this one. Over this one. Over the subalgebra. Here.
The divided powers, but I thought, so even after you specialize Q to be a root of unity,
No.
divided powers are still non-zero, right?
These operators become 0. This is just this one.
Yeah.
These divided powers doesn't become 0.
Right.
So you add as an extra generator in your algebra, in your quantum group at root of unity.
Right. But so UA is by definition is generated by these divided powers.
This one?
Yeah.
No. In principle, no. But you can prove that this one is generated by the case, K inverse, and all the divided powers up to the power of the root of unity. In the root of unity case. In the root of unity case. So something K, when K from K to 1, up to L, when L is the order of the root of unity. This is you can prove this. This algebra in the root of unity case is generated by these guys, and also the Fs. But at the end, the ones that you need is the divided powers of the root of unity.
Yeah, but you define UA as the algebra generated, the subalgebra of U.
Yeah, this one. This part.
Yeah, generated by all divided powers.
Yeah, this one. Yeah. This algebra.
Yeah.
But now I specialize in this. This is a set subalgebra over this. And I replacing the V to the root of unity.
Yeah.
In this case, you just get the divided powers that survive are these ones. This is the divided powers that you get in this new algebra, which is the quantum group at the root of unity. Just in this algebra, you are again in this situation. You are not specializing nothing. So you are the irreducible ones that you are telling me. But when you specialize, you get this situation.
And L3, by definition, is what in this root?
This L3, now as happens in the semi-simple case, you have some Berma modules and an irreducible quotient.
Okay, so
This is the irreducible quotient of this guy, yeah. Because in this picture, this guy is the maximal submodule, so this one is the irreducible. But what happens is that this guy is also an irreducible module of weight 1 now. Mm-hmm. And this one is submodule. This is the quotient. This picture is just saying that delta 3, we have L3 here, L1 here. So this is indecomposable, but you can construct in this way. And there is a relation between these 3 and between this 1, which is a reflection on the Weil group. You can understand all the weights for your module. Okay. So the building blocks in quantum group, in the representation theory for the quantum group at root of unity, are going to be these guys. But these guys are now in the composable, not irreducible. So the standard objects for my UQ, or in general for my category U or finite dimensional modules, are going to be this. Delta lambda. Now, who is lambda? If I'm in the general case of a semi-simple Lie algebra, lambda is just a weight, as usual. But better, in this case, it's possible to prove that I just need integer dominant weights. I don't need all the weights like in the semi-simple algebra. I just need integral and dominant weights. So these ones are called standard modules. And you can think in standard modules just as the quantizations of the simple modules, but now they become in the composable. You can consider duals of these guys, which is just this. For duality, I need the Hoff structure on the quantum group, but because I'm not going to use it in the rest of the talk, just this dual, this is called the co-standard module. And we have also the simple modules. What's happened is that simple modules are quotients of the standard modules and are subobjects or co-standard modules. This is not exact sequence. This is not short exact sequence. This is just, I have a surjection here, an inclusion here. And this map, when I compose it, is usually denoted by C lambda. The properties of this map is that, nice property between these two guys, is that there are no extensions between them. In my category, if I put this, lambda, nabla, mu, this is equal to delta, lambda, mu, C lambda, if I is equal to 0, or it's equal to 0 if I is different from 0. So there are no extensions, and there are just maps when lambda and mu are the same, and the generator, the home between these two guys is generated by this composition of these two maps. So these are the main objects to understand the representation theory, and one extra, which I'm going to define using these two guys here. I want to say something else maybe on this. I think this is enough.
One more question about that. Did you also include the divided powers 2? Like e to the 2?
Yeah. Yeah, e to the 2, it's included in this. This is f to the 2, which is just 2f2. All the divided powers are. But the problem is when you consider the parameter, the quantum parameter, given by the root of the order of the root of the unity. This one disappears, and for that reason you need these ones. But the other guys are, this is f to the 1. Well, this is not f to the 1. This is like 1 f to the 1, which is 1. So this is f to the 1. In this case, you have this kind of thing.
Like F2 would map V1 to V3, for example.
No, because it's just a multiple of this f2. That's the trick. Just this guy are the ones that can jump, let's say, but these are extra generators. You need, in the algebra, U to the A. If you start to working with the formulas, the defining formulas for this guy, you can show that this acting to this guy jumps to here, just in this situation, but just playing with the formulas. But in the other case, because you have this kind of stuff, you are not jumping. Just it's something like, you have extra generators, but they depends, of course, of this algebra U8, of the elastic form of your quantum group. Okay. So with these modules, if I want to produce the so-called fusion category and invariance of manifolds and all of this stuff, we need more extra information. So I need to define something extra, which is called tilting modules. These tilting modules, you can define it in semi-simple algebras, in algebraic groups, and also in these quantum groups, and they are becoming important because with these tilting modules, I can produce a monoidal category, and a quotient of this monoidal category give me all the information that I need. So what is this? A tilting module. T is tilting if it has a filtration by standard modules and another one by co-standard modules. That means I have something like B0 in B1, in BP, let's say, and this is P, and the quotients BI over BI minus 1 is isomorphic to some standard module, so a given way. You need to compute who is this weight. This is not just by free, but you have something like this. And another one, which now the quotient, but this is different, is going to be the co-standard module. Because if you have tilting modules, because the property of the X, the vanishing of the X for T, anti-prime tilting modules, we have that there are no extensions. Between T and T prime, it's equal to 0 for all the i's, different from 0. So there are no extensions between tilting modules, and this is going to be a key property to understand or to relate tilting modules and all the representation theory of these guys with the whole representation theory of your quantum group at root of unity. So this is tilting modules. Why I'm interested in this guy, because some of the standard modules are tilting. And which are the standard modules that are tilting? They are the following. Example of this. If I have, in my root of unity case, I consider the standard inner product in the root datum of my complex Lie algebra. This row is just the half sum of the positive roots. If this is less than L, when L is a simple root, this guy is simple. It's a simple module. Moreover, this guy is its sound dual. This is L lambda, and in this case, it coincides with a tilting module, which I denote T lambda. In the case of SL2, if I start, for example, here is minus 1, I have a third root of unity, so I have 0, 1, 1, 2, and 3. This is my L. In this case, I can put some, let's call it walls. Here is 4, 5. This L minus 1, this guy is called Steinberg module. This is not important for me for the moment. And these two guys, this is delta 0, this is delta 1, are the irreducible standard modules for the root of a third root of unity in SL2. This is called a principal Alkov. Principal Alkov for SL2, and I want to play around with these two modules. I want to understand the tensor product of this guy, the tensor product, the direct sum, a lot of this, because these two are simple modules. A category just generated by these two simple modules is a semi-simple category, but I want to add a tensor structure on this. And for add a tensor structure and a well-defined tensor structure, I need this tilting module. This is the reason for these guys. In SL3, for example, the usual picture for SL3 is something like the root system, is something like this. And I have, these are the roots, let's say alpha, beta, alpha plus beta, and I have the dominant chamber, which is something like this. In this dominant chamber, I can put some walls, and it's defined just by equilateral triangles, and it continues. This part here is the principal, alcove. This hyperplane here will depend on the order of the root of unity. And for example, in the SL3 case, I will have just one module here, one module here, one module here in the third of unity case. And I want to play with these three modules, which are standard modules, inverse modules, co-standard modules, and by definition, tilting modules. And this is the one that I want. There are more tiltings in general for any of these dominant integral weights or any dominant integral weight in SL3. For each of these dots, which is a dominant integral weight, there is a tilting module, which is in the composable tilting module. But I don't want to work with all of these tilting modules, because this other tilting module had a property which is not nice. And this is what I'm going to define. So I want, at the end, just play around with the tilting modules in the principal alcove, which coincides with the standards and the simple module. This is the modules that I want. So some properties of this category of tilting.
So I suppose we wrote there that standard equals co-standard. That's only in the SL2 case.
This is in general. This is in general, because you can fix the duality just by an element and you preserve the weight. But just in this part, when they are irreducible. When you are in the irreducible case for the principal alcove, the dual of this guy belongs again to the principal alcove, and you can prove that they are the same. But you need to fix the duality, because this duality is given by the antipode on the Hopf algebra, but you can also change it a little bit.
Okay.
Just in this, this just happened here in the principal alcove.
Okay.
So this category T, this is a monoidal category. It is closed under core direct sums, tensor products, it is monoidal, and duals. It is a Krüller-Schmidt category, so any T in T can be written as a direct sum of indecomposable tilting modules. And the indecomposable tilting modules are all indexed by dominant integral weights. In general, in any case, doesn't matter. So they are just lambda in P plus T lambda with some power, A to the lambda. So if I think in this, if I have two tiltings, T and T prime, two tilting modules, its tensor product, you can decompose it. If you decompose it, you have two parts. Let's call the part in which this happens, or this region, the principal alcove is just C to the L, C sub L. So you can think in a part in C sub L plus the rest of the decomposition, which is not, call it mu, which is not in C sub L. This part, because all these guys belongs to the principal alcove, they are simple modules, so this is a semi-simple part. But this is not semi-simple. Because in general, these are just indecomposable modules. They could be simple modules. Yes, they could be, when they belong to the walls on this stuff. But I'm not interested in these ones. So what I want to do, if I want to define a tensor product for just the modules here, I could say that if this one is a simple, this one is some delta, I don't know, delta eta, and this is wherever some delta epsilon for eta and epsilon. In the principal alcove, I tensor, because they are tilting modules. I can found this decomposition. And what I want is just this part. If this tensor product of these two is closed, it's because it is a direct sum of elements in the same alcove. So I need to erase this part. So I need to find a property to erase this. And this has a nice property, which is the following, and the one which allows me to erase this part, the non-semi-simple part. There is something called the quantum trace or the quantum dimension, and it's that if lambda is not in the principal alcove, something called the quantum dimension or categorical dimension of this tilting module is 0. These modules are called negligible modules. What's the meaning of this? This is just the usual dimension of the identity operator on this module, but I need to multiply, let's call it 2 rho, for some element. This is just what is called an spherical element. This element depends on the Hopf algebra structure. You can consider Hopf algebras, and you can find some kind of these elements with some properties, and you define a new dimension, which depends on this. For each Hopf algebra, you will get one of these guys, these kind of things. But for quantum groups, you can define a new dimension. Just you rescale your dimension, and this is what it's called the quantum dimension. In general, it's called a categorical dimension. And when all of these guys satisfies this property, that its quantum dimension is going to be 0. So what I want to do is to erase in the category of all tilting modules, to erase all the modules with quantum dimension equal to 0. This is the trick. So I will define a new category, which is called N. Let's call it NT. This is a subcategory of T, and these are the negligible tilting modules. One important thing, I'm thinking in tilting all the time. Negligible tilting, in the tilting category, all of these modules are modules for the enveloping algebra at root of unity, but in the whole category, I cannot do this, just in this tilting category. This tilting category is in the one that I can do this. This has also a nice property. It is a tensor ideal. What means it is a tensor ideal? Well, what the word ideal means. If I consider a module here and a module here, and I tensor both modules, the resulting module belongs to the negligible modules. The modules here has all the composition factors. The indecomposable composition factors satisfies this property. This is possible to say it more general, and that means that any endomorphisms of an object in here, the trace of any endomorphisms, the quantum trace becomes 0. This is the general way to think on this. But for the moment, I think it's good enough just to think in the composable tilting modules. Because this is a tensor ideal, then I can do the following thing. I can consider this quotient category, n modulo nt, and what this means, the objects of this category are all the tilting modules, but in the morphisms, the home in this category from T1 to T2 is by definition the home in the category of tilting modules of T1 by T2 modulo, something I denote n T1 T2, and this is just, I have the objects or the morphisms such that if I go to T1 to T2, the morphisms that factors to any n in my category NT. So I just factor out this guy. If you consider the identity morphisms between this guy, or of course they factor out here, and at the end, what I'm doing in this category is the only object that remains or are different from 0 are the objects which are in this part, in the principal alcove. So this category has the objects, or it is generated by the standard modules, which are simple modules, when standard modules for lambda in the principal alcove. Now I reduce all my situation just to this first part, the modules which satisfies this condition on the weights, this first part in SL2, because starting from this up to infinity, starting from this wall up to you want to go, all these modules has quantum dimension 0. So in this quotient, you have this, but moreover, because this is a tensor ideal on the category T, this quotient, let's call it F in this quotient, moreover, the tensor product descends to this quotient. And it's well defined. You need to prove that this, for example, the representation as direct sum of the part in the principal alcove plus the part which is not in the principal alcove is canonical, but this is possible to do it. But the nice thing then is that just the idea is that if you have two modules, in principle, this is the sum, let's call it eta, in CL. These are the simples, eta, with some power, plus the negligible part what I'm doing in this category now, when I take the quotient, I consider a new tensor product, which is called the reduced tensor product. Then I put the bar, and what I'm doing is just to erase this. So now my tensor product of those two guys in the principal alcove becomes semi-simple, and this is what I want to do. This category, F, which is this quotient category, is monoidal category. It is closed under direct sums and duals. It's closed under tensor products. This is a monoidal category. It is rigid category, rigid monoidal tensor category with unit object. The unit object is just this, which weight 0, and with finitely many simple objects. With these conditions, this is what it's called a fusion category. In this case, it is possible to prove that this is more than a fusion category. This is something called a modular category, and in this case, you can produce the invariance of three manifolds, and that was the motivation. But we want this fusion category, and for this fusion category, if you take the Grothendieck ring, is the one that is called the fusion ring. And at the end, you want to assign these two guys. And the structural constant in this, how are the tensor products, how can you decompose all of this stuff, who are these multiplicities, and this is based in Kasdan-Lustig theory, but you can do it. The problem, just now to show you, when this word arises, is the following. I'm going to start with quantum groups. All of the story to land with tilting modules. All of the story to say that there is a tensor ideal of negligible objects, and the quotient is fusion category. The nice thing of the quotient, because you can do the quotient in many other categories, the nicer thing of the quotient is this part, which allows to get the fusion part. Finitely many simples. For that reason, you consider just the principal alcove, finitely many simples, and you want to play around with these guys to produce something like this. So you can ask, what if you don't start with tilting modules? Because maybe there are other algebras, other Hopf algebras, more general Hopf algebras, which are called spherical Hopf algebras, in which you can define a trace, notion of trace. And if you have another Hopf algebra or category representations of more general categories in which you have a notion of trace, then you can say when an object has trace 0, so dimension 0. So you can say when an object is negligible. So you can take the quotient. What happens with these new quotients in general, not just in this specific case? What happens is the following. If all of this is still true for the complete category of finite dimensional modules. So if you consider the category of finite dimensional modules, and you do the same, because in this category you can define these kind of things, there is no problem. But for n, let's call it this n, all negligible modules, not just the tilting ones, but all negligibles, all negligible modules. This category, you have tensor, you have direct sums, you have these properties, but usually it has infinitely many symbols. All the indecomposable modules with quantum dimension different from 0 becomes a simple object in this category. So this is not usually a fusion category. So with these categories, you don't have the hope to produce invariants or trimanifold or some more structure like in this situation. So the question is, can you do the same without going to this quotient? This quotient is called the semi-simplification. This is highly studied right now. But I want to do the same construction similar to that one without tilting modules. But at the end, I want to get, again, finitely many objects. And that's the reason I want to use the right categories. So the question is, can we do the same without tilting modules? More intrinsic construction that depends in the whole category. And why without tilting modules? Because tilting modules are really special on this kind of categories. They are not possible to define in more general categories or Hopf algebras or something like this. What you can define is the quantum dimension or the quantum trace in some specific categories. And the key idea for this is the following. The key idea is the following theorem, which relates the tilting modules and the finite dimensional modules for the quantum group are root of unity, which claims that the homotopy category, this is the category of chain complexes up to homotopy and bounded homotopy category is equivalent to the derived category of all representations. With this equivalence, I can say, okay, then you don't need to work with T, you can work with U, and then put all this information in chain complexes and see what happens. So this theorem is given by Beilinson, Berzukavnikov, and Mirkovich in a geometric proof, but you can prove also in the case of quantum groups in algebraic terms. And with this equivalence, you can do the following. I have tilting modules inside my category of negligible tilting modules inside my category of tilting modules. So I want to consider the homotopy category of negligibles and the homotopy category of tiltings. So I'm thinking in this side. If I do the same quotient, and I want to do this quotient, KB T modulo KB of NT, and to understand this quotient, how it relates with the usual fusion category. The advantage of this quotient is now I can erase this KBT to DVU. And then I want to replace this guy for something more intrinsic, depending just in the representation theory of my quantum group. So some properties of this kind of quotients to show you how can I erase tilting modules. So this category, let's call KBT, this equivalence, let's call it gamma to dv u. So what I have is the following. here the image of KBT. It's denoted like just the triangulated category generated by the negligible object. And you can prove that this guy is closed and retracts. Any direct summand in an object of this is again a negligible tilting module. This is important because now this is also, we have also a tensor product here. These are not just triangulated categories, these are also monoidal categories. This category, I will denote it when it is closed and retracts for a monoidal category, I will denote it like this. And this is just the tensor ideal. That means, tensor product with any module in the whole category remains here when I tensor with a negligible tilting. This is a tensor ideal closed under direct summands. And so under this equivalence, I can construct this quotient. This is a quotient of triangulated categories, the so-called Verdier quotient. It's going to be equivalent to the quotient of the derived categories of all modules given by this tensor ideal. In this side, we have tilting modules, negligible tiltings. Advantage of the other side, now I have all the modules for the quantum group, again negligible tiltings, but don't worry. If I now, this is not a semi-simple category, this is a Verdier quotient of triangulated categories, this is really big category, but the nice thing is that you can prove that this category is again generated as a triangulated category by the modules in the principal alcove. The same happened with this one. So the Grothendieck ring of this guy and the Grothendieck ring of this guy, which is the same, is just the usual fusion ring of standard quantum groups without the construction. This is just the usual fusion ring. So in some sense, what I'm doing is I cannot produce the fusion category, but I can produce it's a structural constant. I can produce the ring, and with the ring, try to reproduce what is happening. Problem, again, if I want to erase tilting, I have this NT here. So I need to erase it. And it's possible to prove the following nice theorem, which is the following, that
basically, so the homotopy category is category of chain complexes modulo chain homotopes.
this one, yeah. Chain complexes modulo chain homotopy.
Okay, yeah. And your right category is modulo
Quasi-isomorphism. In this one, I invert all the quasi-isomorphisms. This one, in the right category. And this is where the equation in just conceptual way. I'm killing all these guys, but this is just the universal category such that this category becomes zero in some sense. And the same for this one. Or, in other words, you are inverting all of the guys here, in this. All of the possible morphisms that appear in these triangulated categories, you are going to erase it. When I say generated as a triangulated category, is not so complicated, but it is sometimes.
But the quotient doesn't use the tensor structure in any way, right?
No, in this one, no. I'm using just the quotient as triangulated categories. But the tensor product descends on this one. Because this one is monoidal, this one is monoidal, this is a tensor ideal. So as a monoidal category, this is again a monoidal category. And this is nice. And they are both, well, they are equivalent, are generated by the modules in the principal alcove. They are not semi-simple categories. For that reason, they are not fusion categories. They are triangulated categories. They have, in some sense, more information than the usual fusion category. But the fusion rings, the Grothendieck rings of these categories coincide with the usual fusion ring. And that is the nice point. In the case of quantum groups, it is possible to prove a theorem that this guy, this tensor ideal, which is closed and retracts and generated by all the negligible tilting modules, this is equivalent to the tensor ideal in the derived category, close under retracts, and generated by singular or by modules with singular weights. By modules, I can say by the simple modules with singular weights. What's the meaning of this? If I have, for example, in SL3, the dominant chamber given by the action of the while group, if some decomposition of this dominant chamber like this part is the principal half. So all the modules that generate this derived categories and the fusion category belongs to here. This ideal, which is everything that is not in the principal alcove, is above this line. So you can start to thinking in the simple modules which has weights in these walls. And all these simple modules also in this part of the walls. All these simple modules with weights in the walls are the so-called modules with singular weights. And all these modules generate this ideal as a triangulated category. With these modules, what I'm doing is I don't need negligible neither tilting. I just need to understand the singular modules in my category of representations. So what I'm saying is now this category, let's call this, I don't know, dv singular modulo this one. It's a category independent of tilting modules, independent of negligible tilting modules, moreover independent of negligible modules, which produce me the same fusion rings for the tilting category. This is a really nice category. With this category, at least in the case of quantum groups, we can solve the problem of the tilting modules, but depends a lot on the representation theory of the category. So I need similar categories with this kind of a structure of highest weighted structure as semi-simple complexity algebra, algebraic groups or something like that, to define these kind of things and try to understand it. But in subpartial answer to what's happening. So you can say, okay, this depends on the representation theory, but could you erase that representation theoretical part and more tensor product part of the category? So can you do the same just using the notion of tilting? If you have this kind of elements, this kind of traces, can you do the same in the right categories? So the question is the following. If n, as I just erased, are all tilting, sorry, are all the negligibles of the category of finite dimensional representations, in the usual case, this has infinitely many simples. So can you do in the right category terms to understand what happened here? And the tensor ideal, using the tensor structure it is, by the tensor ideal generated by all the negligible modules. Could this category be equal to this, equivalent to this category? Does this category has the same Grothendieck ring? Problem, and this is nice to try to think in these terms, the big problem here it's hard to know if this ideal of negligible objects is the whole derived category or just coincides with the ideal generated by the negligible tiltings. This is not easy to know. And this is the big problem in this definition, with these two general definitions. But this is something to try to study. What, in some categories of representation, can you compute this explicitly and get similar constructions? In the case of quantum groups of this kind of quantum groups at root of unity, which is sometimes called also the big quantum group, at least for me, this is really hard that I don't know. I have a criterion when this is true, but I don't know. But I can apply this definition to other categories of representations. And in this case, just to finish with this maybe, I can apply this new definition, or this quotient, just not new, this quotient, to one specific subalgebra of the quantum group, which is called the small quantum group. There is subalgebra. So this, in general, let's put it here, this, all the derived category modulo this ideal when this is different from 0. If this is different from 0, it's the analog of a derived fusion ring, and its Grothendieck ring is like the analog of a derived fusion ring. Sorry, this is category. This one is ring. So I want to compute these guys. In general, it is too hard to do it, but there is a subalgebra. For this big quantum group, there is a small subalgebra, which is called the small quantum group. And for this subalgebra, this is just generated. It is possible to define as a subalgebra or as a quotient. I'm going to think in it as a subalgebra. Is generated by the k's, the is, and the f's. Without divided powers, nothing of this. It's just generated by this one. This is finite dimensional. This is the nice of this one. This is finite dimensional. And we have also tensor product here and modules reduced. For example, for a simple module here, for a lambda, a simple module, I can decompose this lambda like lambda 0 plus L lambda 1. What is this? This is just the division by L. This is lambda 0, belongs to the principal alcove. And this is an extra module which I can add to get the lambda. And there is a theorem which says that this is isomorphic to L lambda 0 tensor, this guy. When I think in the small quantum group, and I think this module, I reduce it to this subalgebra, this guy, the small quantum group UQ acts trivially on it. Moreover, for the small quantum group, this guy is just isomorphic to C to the dimension of it, the dimension of this L. This is because, for example, in the small quantum group, I have this relation. This k to the L is equal to 1. In the big quantum group, it's k to the 2L is equal to 1. But it is possible to show this. The small quantum group acts in a trivial way on this part. So this module, this L lambda, when reduced to the small quantum group, just become L with an index in the principal alcove and here dimension of L lambda 1, which is the dimension of this part. So all the modules are like this, are indexed by the principal alcove. There are more extra relations in the small quantum group, but I don't need it right now. But this, what is the nice thing of this is the following. If I think in the Grothendieck rings, I have the category of representations, the functor u, and I can send the modules to u, little u. This is just finite dimensional representations for the small quantum group. I induced the Grothendieck ring of this category. I can send it to the Grothendieck ring of the small quantum group. And some people is interested in this ring. In particular, Anna Lechowska, she tries to study this ring, and there are some relations of this ring and some projective modules on the small quantum groups, which it depends on the characters of this module. The usual Weil character, she wants to understand how this character generates this ring. She gave a description of this ring in terms of the of this quantum group, she shows that this K0 U is isomorphic to the usual fusion ring for the big quantum group tensor over the Grothendieck ring of the big quantum group with the small quantum group. This is small, and this is the big one. This is something that she computes. It's possible to compute this kind of thing. Let me just check. I can put complex coefficients, tensoring just by complex number, but she proved this kind of equality. I'm doing this in the piece. She considered the Grothendieck ring of the small quantum group tensor with the usual fusion ring, and this she found, this is something that she calls the Berlinde algebra for the small quantum group. The usual Berlinde algebra is just the algebra of characters for the simple modules, which is coincide with the usual fusion ring for the big quantum group. But she just showed that there is a relation between characters for the irreducible modules in the small quantum group, the fusion category for the big quantum group, and she can do it this. And she says, okay, there is a relation with this with projective modules, but there is not clear why this is related with representation theory. If I use this definition for the small quantum group, it is possible. You can think, for example, what happened if you consider the right category for finite dimensional representations of the small quantum group, and you take out all the negligible modules for the small quantum group. Some tilting negligible modules reduced to negligibles in the small quantum group, but tilting modules in general, negligible in general, I don't know how they restrict to the small quantum group. But you can compute this, as I suggested in this case. And the Grothendieck ring, if this is different from 0, which is a purely representation theoretical object, if this is different from 0, then this coincides exactly with these Berlinde's algebras of these rings. Again, problem, and is this different from 0? And it's possible to prove it. In the case, but just in one case, because now I tell you, if my Lie algebra is the simple one, SL2, this is true. The proof just for SL2 depends in the understanding of all the indecomposable modules for the small quantum group of SL2. And as far as I know, just this is what is known about quantum groups are the indecomposable modules in more general situation. There is no a list of indecomposable modules for SL3 or for type A or nothing like this in a small quantum group are root of unities. And we need this to exactly prove that this is a proper ideal and this quotient is different from 0. But in SL2, it is okay, it is true. If this is different from 0, it is possible to prove that this is going to be the case. But for the other Lie algebras, we need the list of the indecomposable modules for the small quantum group, which is don't know as far as I understand. Neither in SL3, just in this small case, it is known. So this is one application of these new big quotients to get known information, but in more representation theoretical flavor, not just like an analogy that is happening. So this is a partial answer to what is happening. What's next? Change this not just for the small quantum group, for any other Hopf algebra, spherical Hopf algebra, and try to compute this guy. Because at the end, this guy has, in the Grothendieck level, finitely many simples, and this is what I want. Not just infinitely many, as in this case, which is the semi-simplification, the usual semi-simplification. So this is just new attempts to try to understand these fusion rings without tilting modules. Why? Because tilting modules are really special of big quantum group, but they are not available in other Hopf algebras or categories of representations. So maybe with this we can try to do. Again, problem, this ideal is really hard to compute. This kind of tensor ideals in the right categories are really hard to compute. But if you know enough information about the structure of your algebra and your representation, maybe it is possible to do it. So I think I can stop here, and that's the construction that I want to show you. Thank you.
looking at the second line, so the intuition for the algebra is it's like the fusion algebra, but for the small quantity.
Yeah. She considers the usual Berlinde algebra. And the usual Berlinde algebra is just the fusion algebra for the big quantum group.
Big quantum group.
The big, yeah, the F. It coincides. But, and this, she related also with the characters of the simple modules in the principal alcove, and that's it just in the case of the big quantum group. And then she considered the restriction to the small quantum group, like in this.
Yeah, but here, so I thought, so F is the fusion category for the big quantum group, right?
Mm-hmm. Well, indeed, she proved something like.
So I thought it looked like what this is saying is that so you have F, which is fusion category for the big quantum group, V, which is fusion category for the small quantum group, and then that first line is saying you get V by just tensoring, taking the fusion category for the big quantum group,
yeah,
and
but,
tensoring over the.
But the problem is, well, this is not just by free. Yeah, it's not by free distance approach. This is. What is the best way to write this? This is some. I need to consider this one, but I also need to take some action because in the small quantum group, now the action, the dot action given by the usual weights reduce. So some modules collapse, start to collapsing in this kind of quotient. So not exactly this one. When I reduce this to the small quantum group, there are more relations between the simple modules. And these more relations is because we can now, in this, it's possible to define it also as some ring, modulo some idea of relation, which is, I don't remember exactly, something like lambda, it's minus delta lambda big dot, sorry, like omega. She defines another action, big dot lambda, and this big dot lambda is like usual dot action by taking modulo. This big dot action is taking modulo, sorry, take this one modulo, the usual dot action, taking modulo LP. Then I need to take some extra information. And this is what remains in this one. This remains in there are more information in this that I'm not writing right now here. But at the end, it's kind of this tensor product, but with extra information. What she showed is that this kind of Berlinde is a quotient given by some extra action that appears in the small quantum group. What it's possible to do is that consider this category of representation and this quotient, at least for SL2, coincides with the ring that she considered. But there is extra information that I'm not writing in here.
So this is saying that if you look at the standard modules with weights related by the dot action, when you restrict to the small quantum group, they become the same.
Yep, yeah. Some modules collapse, some modules becomes the same.
So is this?
There are more extensions. You can compute more extensions that appears in this situation.
Yeah, okay. But is this related to Hamiltonian reduction?
I don't know. To be honest, I don't know.
Is it kind of something for vertex algebra? Something similar happens. You have affine vertex algebras and Hamiltonian reduction. You get W algebras, and it takes modules for the affine go to the same central character to the same module for the W algebra.
Could be similar. To be honest, I don't know. We can check, but I don't know. But in this case, for the quantum group, some of the modules, of the simple modules and also projective modules, there are some collapsing process happens when you reduce. Because of this theorem, this is the key. You are erasing of the modules which are multiple of this in the weights. So some things start to collapse.
Okay. Yeah, it's very interesting.
So, yep.
Thanks, speaker again.
Thank you.